Okay, so today let's get into a little bit of alternating current. So with alternating current and voltage in general, we deal with direct current DC and alternating current, which is AC. Okay, so what we need to remember when it comes to terms of DC and AC is that we are dealing with current, the flow of the electrons. Okay, with DC current, we have to remember that the electrons are going to flow in only one direction. A good example of a DC circuit is a flashlight, 9-volt battery, or your C batteries, D batteries, AA batteries. Those are DC current. They're flowing in only one direction. Alternating current, it flows back and forth from positive to negative, back and forth, back and forth. So when the electrons are reversing in direction of flow at regular intervals, we now know that as AC, or alternating current. Okay, DC current is not as common as AC because it's only used in certain applications. Like I said, like a flashlight, something very small. But most of the current produced by electric utilities is in alternating current. One of the big benefits of alternating current is that it can be traveled for a much further distance without having to be like regenerated, power boosted, and all that stuff. If we had DC current, it would have to be sent into substations like maybe every couple of miles, where that power would now be kind of like regenerated and then sent out further down the line. Most of the equipment in HVAC industry runs on alternating current, as do pretty much everything in a home. Works off of AC. One of the other benefits of AC is obviously money. It's cheaper and more trouble-free than equipment that runs on DC. Since it is used more widely, we need to make sure that we understand the theory behind how it works. We need to be familiar with the way it is distributed by the power companies. So alternating current, or AC for short, is an electron flow that alternates. Okay, the electricity flows in one direction, and then it flows in the opposite direction at regular intervals. Now, AC current is produced by cutting a magnetic field with a conductor. Now, we can look at that magnetic field and how it flows through a sine wave. Okay, a sine wave is used as a graphical representation of AC current. So here's an example of what we're talking about, a sine wave. When electricity is at rest, we are at zero. It doesn't move, right? But once we start to make electricity flow in, especially in AC, it literally is nothing more than a gigantic circle. It has a starting point, and then it rotates, and then it goes back to its starting point. Okay? These lines represent degrees. So at its starting point, it's going from a positive, and then it comes back down at about 180 degrees, and then it comes over here to a negative, and then it's at 360 degrees. So 360 degrees is basically a full circle. So this happens every couple of like 60 times in 1 second for 60 hertz type appliances. So when the conductor rotates through one complete revolution, it generates two alterations, or two flows. Okay, one flow is going to be positive, the other flow is negative. So one cycle occurs when the rotor or conductor cuts the magnetic field of the north and south poles. The frequency of AC is the number of complete cycles that occurs in 1 second, which is better known as hertz. Okay? but can also be referred to as cycles. But more commonly, when you look at a motor and compressors and stuff like that, it's going to have a hertz rating on it. Okay, the common frequency in the United States is 60 hertz. Some other areas and in foreign countries have 25 hertz that's used. Okay, 25 hertz cycle can be used by the human eye in light fixtures. So 60 hertz frequency is the most common, but 50 hertz can also be used in some cases. Now, in regards to phase of your AC circuits, the phase of your AC circuits is the number of currents alternating in different time intervals in that circuit. So we have two types of phases that we run into a lot in HVAC, your single phase and your three phase. With single phase, it's going to be flowing in only one, has only one current. It only goes really like from positive to negative, and that's really it. With three phase, you have technically three phases of current that's flowing at different time intervals at a given point. Okay, alternating current is available in several different voltages with different current characteristics. Some of the most common here, as you can see on the screen, is you got 230 volt single phase, 60 hertz, 230 three phase, 208 three phase, 460 three phase. So some of those are your common voltages that you'll run into, especially like with rooftops, units, heat pumps in some cases, where you'll be running into those types of voltages. So here's the sine wave of a three-phase alternating current. This is where we were talking about where we actually have pretty much three legs of power that are being sent into this unit, but they don't ever cross, or they don't interact with each other, so to speak. They are all 180 degrees out of phase with each other. Okay, so here's your phase one, this blue one. It's going from positive to negative 60 times in 1 second. Maybe here's your phase two, again, which is out of phase with the first phase. They do not ever cross. Okay, once they pass this line, or what we call the common, that's really where it kind of alternates from that positive to negative. But since we have three legs of power on there, they do not necessarily ever really cross each other at the exact same time. Okay? So because AC starts at 0, it reaches a peak and then returns to 0. There is always a variation in that voltage, and an effective value has to be determined. AC current reaches a peak at about 90 electrical degrees. When you turn on a, say, a three-phase unit, and you put your amp meter on one of those phases, once you initially turn on that phase, you're going to see that there is a higher voltage for maybe a brief second on your meter. That's that peak voltage that we're discussing here. It's because that power has so much electrical energy that once it's released, it kind of just shoots out into those wires. But this only happens for a brief second, and that's what we call that peak voltage. We could measure that if we were to put that unit on a sine graph and actually watch the electricity flow through it. But we can normally see that when we are using just a standard voltmeter. It happens for literally a brief second. Okay, that voltage is known as the peak voltage. Okay, the effective voltage of an AC current is 0.707 times its highest or peak voltage. And the same applies for the amperage. It's also 0.707 times the peak amperage. Okay, all electric meters are calibrated to read the effective voltage and the effective amperage. So AC current is produced by an alternator, or a generator, basically. Okay, the alternator is made up of windings, or a set of windings, called the stator and the rotating magnet called a rotor. The number of windings used depends on the desired phase characteristics of the current, and when the rotor is rotated through the field of the windings, an alternating electrical current is then produced. So, single-phase current is produced by an alternating with only one winding on the stator. So if you look at this diagram here, this is basically a single-phase motor. We have a positive and a negative. Electricity flows through each one of our windings, and as we energize these windings, we generate a magnetic field. That magnetic field will now in turn turn the rotor. And when I turn that rotor, I am now able to generate a magnetic field and produce electricity. Three-phase current is produced by an alternator with 3 windings in the stator that are wound 120 degrees apart. So each one, again, these lines, A, B, C, each one of these legs is 120 degrees out of phase with each other. This is where we say that each one of our windings will operate at different time intervals, 60 times in 1 second. So which means 60 times in 1 second, one of these legs will technically become a neutral. But it happens so fast that we are not necessarily able to pick that up. Okay, inductance in reaction. In reactance, it's a common assumption that when voltage is at its strongest, amperage is also at its strongest. This is not always the case. Amperage of a circuit determines the strength of the magnetic field in that circuit. So as we increase the current and we add current to it, we will now increase the magnetism. The magnet will now become more powerful. And the same applies if we were to decrease the current going through there. The magnetism will also become weaker. Okay? The fluctuation of the magnetic strength in an AC current circuit in conductors cuts through more than one magnetic field. And when that does it, it induces a voltage that interacts the original voltage. Okay, so when we look at this is what we're kind of talking about here. This is the effect called inductance. So as this motor is spinning, each one of those phases are now out of phase with each other. See how that graph is kind of moving. Not one of those phases will ever cross at the exact same point or at the exact same time. Okay? The inductance of an AC circuit is the effect of the magnetic field, which produces an out-of-phase condition between the voltage and amperage. Okay, AC circuits are affected by resistance. It's just like everything else in an electrical circuit. It depends on how much resistance is in that load, is how it's going to affect how that unit works. Okay? Reactance is the resistance that AC encounters when it changes flow. There are 2 types of reactances in an AC circuit. You have inductive and capacitive reactance. Inductive reactance is the opposition to the change in flow of alternating current, which produces an out-of-phase condition between voltage and amperage. Your capacitance reaction is caused in AC circuits by using capacitors. Okay, when a capacitor is put into an AC circuit, it resists the change in voltage, causing the amperage to lead the voltage. Okay, so some of the resistance and reactance in an AC circuit is also called impedance. Okay, since voltage and current are out of phase with each other in an AC inductive circuit, they are not necessarily working together. All right, because remember, those lines do not really necessarily cross at the exact same time. Thus, power of the circuit must be calculated by using a voltmeter and an ammeter. Okay, when we're calculating this stuff, we want to calculate it in watts. How many watts of power do we have? Okay, the ratio between the true power and the apparent power is what we would call the power factor. You may look at some motors and you'll see a little on the name tag there, you may see a little designation of PF. That is the power factor rating for that particular motor. Every once in a while, sometimes you may have to do this simple calculation to see whether or not that motor is capable of handling that so-called power factor for the voltage that is being received. Okay, the power factor is usually expressed in a percentage, X amount of percentage. Okay, the following formula can be used to calculate the power factor of a circuit. Okay, your measured power divided by your calculated power.